Second talk is given by Larson on partition relation perspectives. Please.
It's a real pleasure to be here and see so many familiar faces and to meet new people. I'm very thankful for the invitation. So I'm going to start with relations. And many of you know that I'm very fond of set theory homepages. I have a list which could always use updating, and I appreciate people sending me information about it. So I thought, well, let me go look at Myrna's homepage and see what she's got there. And that gave me the idea of looking at a short CV for Myrna as an excuse to show off some pictures of the very photogenic Myrna. So here we have a picture from Ken Cunin, her thesis advisor's fest. I think it was taken in 2010 during the Cunin Fest. And I thought, this is one of the nicest pictures I know of Ken Cunin. And it's really nice to celebrate the person and the institution that she got her doctorate at. So, and of course, we see a few familiar faces in there besides, with Istvan and Judy Reutman. So for her early career, from 93 to 95, she was a postdoctoral fellow at Hebrew University of Jerusalem. That certainly was a productive time for her. And then from 1995 to 1998, she was a visiting assistant professor at the University of Wisconsin in Madison. And that's actually where I first met her, at least to my memory. There was an annual Association of Symbolic Logic meeting held in Madison in March of '96, and she gave a talk there. I remember watching her give this talk and was very impressed, and I thought, this is one of the people that is going to persist. You know, you look around, you see students. I've already talked to one student here. They expect to graduate within the next year, but they're not getting an academic job, so they're going to do something else for their life. And many people sort of drop off the doing mathematics setup at some point in their lives. When I was a postdoc at UCLA, I talked with Ernst Strauss, who had been an assistant to Einstein, and one day we were sitting there, probably working a crossword puzzle at tea, and he said, well, you know, just because I, as a 26-year-old, decided I wanted to be a mathematician doesn't mean that I now want to be a mathematician. But to be a mathematician, you have to keep choosing it. And that's something that really makes a difference. And Myrna's clearly kept choosing it. So I included the picture off of her webpage. You can see Professor Myrna Jamona of UEA. And this is my excuse to say how much I enjoyed visiting her campus and working with her there. And we had beautiful weather when we visited, so I hope that when you were last in Norwich, if you've been there, that you also had some beautiful weather. I remember walking across this glass bridge, which seemed kind of strange, and there were also, I thought, something that should be spread much wider, which was covered spaces for parking bicycles. It was very good. But and the other thing for me personally was there were lots of things named after Quakers whose names I recognized. That was very nice. So she's a wonderful host, whether she's at UEA or anywhere else, and that's something I expect many of you have experienced. So the next thing I turned to was I thought, well, what about her PhD students? I can go to the math genealogy and find out who they are. And this is a picture of, let's see if I can do this, Katie Thompson and Christoph Weiss. And I thought, you know, Myrna does have an influence on her students. And I met Katie in Wisconsin when she was visiting with Myrna one time, at a time I happened to be there. I think it was probably close to Christmas, because I'm often in Madison close to Christmas. And I got to hear Katie talk. And so here's the list of Myrna students. The only other student that I could find a picture of was Gregor Dolinar. So he's on this list. And the map genealogy didn't tell me where Omar Salim got his degree. Well, then some updating needs to be done. This is the kind of thing that happens. I thought you probably have some in the pipeline, and you're telling me you've already got some out there that. Yeah, so I don't, how do people get there? I mean, you send them in or they send themselves in? It's gotta be something like that, because they want it to be official and correct. So, but you see, they're not all from the same institution. I thought that was pretty neat. And, well, she has, according to the current Math SciNet page, 25 co-authors. And these talks get to be kind of tiresome after a while. So I would like everyone who's a co-author or working on a paper with Myrna now to stand up. Just stand up. I want to give you this opportunity. Come on. Okay. Yeah, you should get up too. Great.
Stand halfway out because I want to be a co-author.
Good for you. Good for you. Yes. Okay. And here we have a picture of Myrna with Grzegorz Plebanek. And he overlapped with us when we visited at UEA, and it was delightful to have him around also. So now we're turning to perspectives. And here I'm going to give you some results of various and sundry kinds. The first one is just one that's a favorite of mine, the Balance-Baumgartner-Heinel-Todorcevich theorem, also called the BHT theorem, because what a mouthful. And it says that for every regular cardinal kappa and every xi less than kappa and k less than omega, 2 to the kappa plus arrows kappa plus xi upper 2 lower k, which means if you take the pairs from 2 to the kappa plus, the cardinal, and you split them into k many pieces, there will be a subset of size kappa plus psi, all of whose pairs are the same color. This theorem, nice statement, but also very nice proof using ideals that come from chains of elementary submodels. And the reason it's here is because Ari Brodsky proved a version of this, generalized it for trees. And he proved that for every infinite regular cardinal kappa and xi with 2 to the cardinality of xi less than kappa and k less than omega, that if you have a non-2 to the less than kappa special tree, then if you split its nodes into, it pairs of nodes into k pieces, you can find a subset that's large where all the pairs are the same color. And to do this, he developed a theory of stationary sets, stationary subsets of trees. I thought that was a really nice thing. Stationary sets are just a really wonderful notion of largeness, and whenever you can get that kind of notion to generalize to another area, you really do something nice. And he also used ideals that come from chains of elementary submodels in his proof. So the next theorem I'm looking at is a theorem of Erdős and Rado from 1956, that enormous paper that had such a big influence. And they showed that the continuum hypothesis implies that aleph 1 over omega does not arrow aleph 1 over omega upper 1, 1, lower 2. So what kind of partition relation is this? It's called a polarized partition. And here theta over omega does arrow theta over omega 1, 1, upper 1, 1, lower 2. Means that for every function c from theta cross omega into 2, you can find a subset A of theta and an infinite subset B of omega, such that the cardinality, such that C is constant on that set of pairs. There are lots of different ways of thinking about this. You can thinking about it as having a parameterized family of partitions or many other kinds of things. They turn out to be nice and useful. And Shimon Garti and Saharon Shala in 2014 were looking at which thetas have this property with in a consistent way. So when can you consistently have it? And they were looking at, they were especially interested in cardinal characteristics of the continuum. They had earlier shown that the partition relation was true for theta less than the splitting number S. And in this paper, they show it's true for the reaping number less than theta. How am I doing on that? I don't know if I put down what those are, but I can tell you if you want to after. Their model has aleph 1 equal the reaping number less than the splitting number equal aleph 2, which is the continuum. And that does it for you. I mean, one pushes things down and the other one pushes things up. So if you just put them in the right order, you get the model you want. But it just has aleph 1 and aleph 2 in it, so you might like something a little bigger. And this plan is a really good one, except it's not known whether it's consistent to have R less than S, the reaping number below the splitting number, and the continuum bigger than aleph 2. So the next result I want to mention is by Claribet Pina. Claribet Pina is a student of Todorcevich who's now in University of the Andes in Venezuela. And she's investigated the reduction of colors type of problems where you're looking at a coloring with some finite but greater than one, a finite number of colors, but you have to have more than one or you can't reduce it. And she's looking at coloring pairs again, only now she's coloring topological spaces. She's looking at ordinals with the order topology on them, and she's interested in finding out when you can get a copy of, and I didn't fix it, omega squared plus 1. It should be omega squared plus 1 everywhere inside those little round braces. So this one needs to be omega squared plus 1. Thought I fixed it, but clearly I didn't.
In the written part, there's also one of those m's should be an L, right?
And one of those m's should be an L. Almost surely. Let's see. I see an L when I'm getting a positive one, and another L when I get a positive one. But one of the n's should be an L. I'm not sure where you're talking about.
So when you say the minimum number of colors, L, I guess, so that if pairs from alpha.
Oh, you're reading my definition, okay? So given countable ordinals alpha and beta, the minimum number of colors needed, so that if pairs from alpha are colored with finitely many colors, at least 2, then there is a topological copy of beta whose pairs realize at most m colors. So I didn't tell how many colors we started with.
Well, as in, so in the definition, there's no L.
Right. I said finitely many colors, at least 1.
That's some L.
So L is finitely many, is a finite number, and it's at least 1. So when it's written down here, I just copied the kind she used, but I personally think of it as less than omega, but then she's being more precise than me because she's saying, it really has to be bigger than 1, or you can't reduce it. Okay? Sorry if it's messed up. I mainly wanted to put her result up because I heard her talk in Barcelona about some of this work. She's been doing a beautiful study of the oscillation mapping and how it comes into this. And that got me interested in the topological partition relations again. I'd read about them in Baumgartner's paper, and I thought they were very pretty there also. And I talked with Bill Weiss about them some. So moving on to a topological pigeonhole principle. Here, present today is Jacob Hilton. And building on the ordinal pigeonhole principle of Eric Milner and Richard Rado, which calculates the ordinal pigeonhole number of a sequence of ordinals, and the work of Bill Weiss, of Pricry and Salovey, and of Shala, Jacob Hilton constructed a pigeonhole principle for ordinal topological spaces. It's pretty long. I wanted to put something in that wasn't going to take up so much of my talk, and so what I did was put in what he wrote was, which he described as his main breakthrough. So I hope I'm correct about that. All right, and I understand your paper is going to appear in the JSL. Good. So suppose you have a list of a finite list of countable ordinals. I think these are countable. Yes. And then the pigeonhole principle of the one more than an ordinal power, the sequence you get by taking one more than the ordinal power of all of these, is omega to the alpha 1 sharp alpha 2 sharp dot 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 sharp alpha k plus 1. So it has that same form, power of omega plus 1. And if I've gotten this right, the sharps mean the natural sum or the Hessenberg sum. And if you think about any ordinal, you can get its Cantor normal form. If you got two of them and you got two Cantor normal forms, by plugging in a lot of things times 0, you can have them have the same ordinal powers, and then you pretend that they're elements of a vector space and you're taking linear combinations and you're adding them up. And of course you always write things in decreasing orders for the ordinals, and out comes something. So did I get this right?
Yeah.
Okay, great.
Can you just tell us what is the pigeonhole principle? What does it
Oh, you divide the points up, right? So the finite pigeonhole principle, they often talk about balls and urns, and how many balls do you have to put in the urns before you can get at least 2 in something. It's the same kind of an idea. You're just partitioning basically the one element sets or the elements themselves into a small number of pieces or maybe a large number of pieces, and you're looking for how big. So the pigeonhole function here, p ord or p top, is computing the smallest number you can start with to make sure one of the cells of the partition has the desired object in it, which for the ordinal one is something that's order isomorphic to that ordinal, and for the topological one is homeomorphic to the ordinal space represented by that ordinal. Okay? And thank you for asking. The other part, which is when you just have ordinal powers, it uses the pigeonhole principle for, and I can see there's a typo there too, uses the pigeonhole principle for the ordinals themselves. You start with ordinal powers, omega 1, omega to the alpha 1, omega to the alpha 2, up to omega to the alpha k. You split a large set into k pieces, and you look for one of those types. It'll work if you take something of the size power of omega, the number you need to do for the ordinal version. Okay? I thought it was nice. So, there's a reason why the powers of omega and their successors appear so often. we say x and y are biembeddable and write x is equivalent to y if x is homeomorphic to a subspace of y and y is homeomorphic to a subspace of x. So one of Hilton's lemmas is that if y is biembeddable with x and xi is biembeddable with ui for all I less than kappa, then the space y arrows topologically, the space is xi. If you're coloring n element subsets of y and you're looking for a topological goal and you color them with many different colors and you've specified xi for the ith cell, that will happen if and only if it works where you substitute v for y and you substitute the ui's for the xi's. So it just carries over nicely. And this kind of arithmetic is nice, and this biembeddability turns out to be useful not only here, but also later. So now we're going to look at topological Ramsey numbers. In their search for Ramsey numbers of ordinal topological spaces, Andres Caicedo and Jacob Hilton looked at two kinds of goals. So a Ramsey number, here again you're looking for the smallest number so that when you partition pairs of a ordinal topological space into two colors here, I think that's what you're doing, then you get one of the desired goals with a homeomorphic copy of the ordinal space you're looking for. They also looked at a second version, Ramsey for closed spaces that are both order isomorphic to a given ordinal space and closed in their own supremum. So we have the pigeonhole principle for the topological spaces, and together they came up with a version of the pigeonhole principle for these closed spaces, and most of it carried over pretty nicely, thank goodness. And the remaining part looked like it came out pretty nicely. Is the argument done and the rest of it parallel, or is it, but do you get a different answer, or?
Well, they come out the same in whenever you have powers of omega or powers of omega
Plus one, which is why those are the interesting ones, really.
Then you just have to worry about. So that the reason they're different at all is because, for example, omega plus 2
Yes, is not one of those nice ordinals.
homeomorphic to omega plus 1. But
Yeah.
It's not.
Yeah. Okay. So they write R top alpha I for I less than kappa for the topological Ramsey number, namely the least ordinal beta, such that if you split the pairs of beta into kappa many classes, there will be a subspace order homeomorphic to alpha I for some I, all of whose pairs of that specified color I. And the same thing goes for the closed spaces. So Erdős and Milner proved the following theorem for ordinal partition relations. We actually proved something slightly stronger, but this is a much more elegant statement. If omega to the alpha, if you split the pairs of omega to the alpha into two pieces, and it turns out that either you can get a subset of size omega to the 1 plus beta in the first cell, or you can get k many elements in the second cell, again with their pairs whose pairs are in the first cell or whose pairs are in the second cell. Then you can split the pairs from omega to the alpha plus beta. No matter how you split the pairs of the omega to the alpha plus beta into two parts, either there's a copy of omega to the 1 plus beta whose pairs are in the first cell, or a subset of size 2k whose pairs are in the second part. So Caicedo and Hilton found a counterpart which they call the weak topological Erdős-Milner theorem, and it's basically the same kind of thing. So, let's see. Up here, we're looking at omega to the alpha. Down here, we have to bump up. Here, we multiply times omega to the beta. And if you look at this, we multiply times omega to the beta. And then up here, we're getting 2k, and down here, we're adding 1. So it's a weaker theorem, but hey, it works. And that's the kind of thing we like to see. And in a corollary to the main theorem, Caicedo and Hilton prove that these Ramsey numbers coincide in certain cases and give upper bounds for them. And here I'm just going to point to the first one here. Oops, wait a minute. Calming attractions, all right. Here. I can't control my fingers. So first is that if you have a countable ordinal, if you have countable ordinals put in, a countable ordinal comes out. That's always nice to know that you don't have to jump way up in cardinality. Then there's some details, and maybe I will skip over that for a couple of questions. So the first question I'm addressing from their paper is there a topological partition ordinal alpha greater than omega? That means, can you find some alpha greater than omega so that if you color the pairs from alpha with 2 colors, either you get a copy of alpha whose pairs, so same guy, are in the first color, or you get a triple whose pairs are in the second color. So there are more partition ordinals than omega for just ordinary ordinals, but can you do it with the topological spaces? And the second question is it possible to reduce the computation of these topological numbers, Ramsey numbers, to a finite combinatorial problem? You can do that for many small cases of ordinal ones. So it would be nice if you could do that. And now we turn to the Halpern-Wechsler theorem. This is a really beautiful theorem, and I asked Bill to cut a picture out of Stevo's book because he has a really nice illustration of what k-dense sets are and k-extense sets are, and a k-dense, so it's a subset of a finitely branching infinite height, no end, no tree tops, right? They go on forever. And you're interested in looking at things where you have a level k, and then you take everything on level k and you extend it up, and you'll hit the set xi, the set x. So a k-dense matrix for a product of trees is a product of sets xi, where each xi is a k-dense matrix. So it's the guys that are above, the set of things on level k that still survive in your tree because you keep taking subtrees, and they just wander around. And then the second kind, you have this k-extense matrix where you specify that you're in a subtree that starts above a point. If you're going to put a lot of these together, it certainly makes life a lot simpler if the stems of the trees get longer and longer. So an asymmetric version of the Halpern-Wechsler theorem, this is Stevo's title in his Ramsey spaces book, for every coloring of the finite product of finitely branching trees, product I less than d ti of this is a partition, k0 union k1. Either k0 contains a k-dense matrix for every integer k, or there's some x in the product so that k1 contains a k-extense matrix for every integer k. I'm bringing this up because one of my favorite problems is Laver's conjecture, and Laver looked at level sets. So he didn't look at the ones that are going jig-jag, jig-jag in his paper where he did the perfect set, perfect tree version of the Halpern-Likely theorem. And so I put level sets all over the place. I'm sure you would have loved any kind you could prove. And when I talked to him, he talked about the stems growing and stuff like that. So for every level set coloring of the infinite product of downwards closed perfect trees, product I less than omega ti, split into two parts, k0 and k1, there is some j less than 2 and some x in the product of all the trees, so that for each k less than omega, kj contains now x vector dense level set matrix. So you're now taking an infinite product here of these guys. So, that one's been around for a while. I really like it. I hope somebody solves it one of these days. And now we add Myrna to the discussion, and by that we mean let's look at our work with her and with Bill Mitchell. So a theorem that we looked at in generalized, because you can see that's my pattern. Let's give the version that was known and then what comes later, is that if you partition the n-element subsets of the rationals into finitely many pieces, then there is a number Tn where you can shrink the number of colors down to Tn. And you can't shrink it down further. There's a coloring that prevents that. And furthermore, we can say what Tn is the nth tangent number. So Dennis Devlin was a graduate student of Jim Baumgartner at Dartmouth College, so one of my mathematical brothers. And for regular cardinals kappa, there's a natural order less than or equal to q, extending the lexicographic order on kappa greater than into 2, such that q kappa, which is that tree of height kappa, which is less than kappa, which is a complete binary tree of height kappa, is a kappa dense linear order with this particular linear order. And Bill Myrna and I proved in 2009, well, that's when it appeared, that for every positive integer m, you can find t plus m less than omega, such that for any cardinal kappa, which is measurable after generically adding lambda many colon subsets of kappa, where lambda satisfies the partition relation that if you split its 2m tuples into 2 to the kappa pieces, you can find a subset of size kappa, all of whose 2 to the m element subsets are the same. The kappa dense linear order q kappa satisfies q kappa. So if you divide the m tuples of q kappa into finitely many pieces, and I see the kappa is interrupted by an extra parentheses there. Sorry about that. So you can reduce the colors to t plus m, but you can't reduce them further. And t plus m is the cardinality of a finite set of trees, and we don't have a nice description of that, but it grows pretty fast. So down here at the bottom of the slide, for m equal 3, for m greater than or equal to 3, the value you get with the plus on it is bigger than the value you get without the plus. So T3 is 16, and T3 plus is 20, T4 is 272, and T4 plus is 776, and then T5 is 7,936, whereas T5 plus is 151. 1184. And after that, I don't dare say the names because I know they're spoken differently in Europe and in America. So, and I don't really know either convention very well. All right, so this is our theorem. And a key tool in it is a theorem by Shala, which he gives a sort of a Chinese menu of different possible options, of different hypotheses that you might want, and then sort of, gives you an assemblage of proof so you can mix together to get the answer. And he calls it something like a generalization of the Halpern-Leuchtley Pincus-Lever theorem as influenced by Harrington's proof or something. It was a very nice long description. So we used we picked and chose and we came up with this particular version, and I hope I got it without any mistakes. And we talk about it in terms of embeddings, and it is a generalization of Halpern-Leuchtley, which is my other excuse for including the Halpern-Leuchtley theorem in earlier. So I'm just kind of leaving it out there. It's sort of messy to read all at once, so don't worry about it. Based on work by Heinel and Komja, the positive partition relation for Q kappa does not follow from any large cardinal hypothesis on kappa. So I thought this was a nice thing. The hypothesis in our theorem comes from Shala's theorem. He needs that in order to make his proof work. But it's a pretty natural question to ask, can you just get it from some large cardinal hypothesis? And the answer is no, because Heinel and Komja have a forcing of size aleph 1, which adds an order type theta of size aleph 1, small, with the property that psi does not, if you color the pairs from any psi with omega 1 colors, you can't get rid of anything, no matter what psi is. So that's a pretty strange thing. And it says you can't, because that doesn't go away. That says you really can't get a large cardinal that will do the job. Our proof uses the theorem of Shala, quoted above, to show that all the types we say occur do occur in every large set. So the question that one might ask is, does the negative partition relation, which is just really talking about every time you take a big subset, does this particular thing have to be there? It's a finite little guy. Does that hold for all sufficiently large, for a tail of M? For some regular cardinal which doesn't satisfy this hypothesis, but is bigger than our nice Q, which we're modeled on. So I just put that out there. It would be nice to know we do use the theorem of Shala in our proof that the finite types all occur, and there are more of them than occur in the situation with Q. All those ones that occur in Q, they have to occur here also. But we have these extra ones, and you can make that partition. So that's not the only thing that we worked on with Myrna. We've had many wonderful conversations over the years in cafes and different parts of the world. And I wanted to say how much I enjoyed working with her on Mary Ellen Rudin's last writings. I thought that was very nice. An example of just a brief example of the breadth of the kinds of things that that Myrna has done. And then I have a bibliography, and finally I say thanks, and this is something that Myrna knows about. So thank you very much.
questions or comments? May I ask about the Q kappa, which started to occur somewhat? It's kind of not unique in any way, but you talked about it as if it's unique, right? Q kappa, if you go back in your slides.
Yes, let me go back in the slides.
Okay, back.
No. Q kappa
is it-
occurs
oh,
here.
It's a
aha,
concretely
you-
defined.
Okay, next one. So here you defined it actually. Next one.
Next.
This is the theorem.
No, it must be before.
Before.
It's before.
Okay, so okay, now you define it.
Yeah,
Okay,
here.
so
Yeah.
call it. Okay, fine. Yes. Question. That's a perfect answer. Yes.
Okay, that answers your question
Yes,
because
that answers the question.
didn't
Yes.
give you enough time on that. That's okay.
Maybe I can.
Yes. Nella?
Yeah.
So I just mentioned something that we haven't worked on, but maybe it's interesting. So with Bill and Jean, we worked on some generalizations, analogs of this result with a random graph. So you can have a random graph which has a saturated structure, etc. But we haven't looked at this in general. So maybe there is some theorem that can be proved in general for saturated objects with this kind of cardinal assumptions. I think that might be a nice theorem because we got the different numbers for the graph. Of course, you can tell that it is G if you got the numbers. I would never be able to do that. But I think there might be some partition theorems for saturated structures in general.
I had never heard of uncountable ultra-homogeneous structures before coming to this conference. It never occurred to me you might think about that sort of thing. So I was very pleased with that, and maybe there is something to look at there.
Other questions?
Is Lever's conjecture still open?
Excuse me?
Lever's conjecture.
I believe Lever's conjecture is still open.
Okay, if no more questions, then let's thank Tri again.